Today, we're going to talk about the outer solar system. But before we do that, there are a couple of concepts that it would be useful to go over. The first of those is the Roche limit. This is the radial distance from a massive object, like a planet, at which tidal forces exceed the gravitational force necessary to hold bodies together. You could think of this as the boundary at which moons become rings. An equation for the distance d at which the Roche limit is from the center of a planet. We're not going to derive this equation, but we can apply it for the planets, is the cubed root of 9 times the mass of that planet divided by 4 pi times the density of the moon. We can see in this sequence of illustrations that a moon gets closer to a planet, the tidal forces increase. That's why in the second panel, the shape is distorted. Then as it crosses the Roche limit, that white boundary there, it starts to be torn apart. Then, due to Kepler's laws, what's closer to the planet will orbit faster. So then it gets torn by Keplerian shear and soon becomes a set of rings, many small particles. Of course, a moon would not instantly get torn apart. It would depend on how long the moon stays inside the Roche limit. So if a moon is on a highly elliptical orbit, it could pass through inside the Roche limit. But if it stays inside for long, then it will get torn apart. Another concept I want to introduce you to is the Hill sphere. This is the region of gravitational influence or dominance of a body. So the moon orbits the Earth because the moon is inside the Hill sphere of the Earth. The Earth orbits the sun because the Earth is inside the sun's Hill sphere. If there were a satellite orbiting the moon, it could do so close enough to the moon. Now, those orbits would probably not be stable for long, but they would still be orbits around the moon. This image shows Roche limits and Hill spheres of the sun, Earth, and moon. Of course, the sun's Hill sphere extends way beyond the Earth, and so these are not to scale. But it gives you a general sense that inside the Roche limit, there might be rings, and there can be moons in between the Roche limit and the Hill sphere. But outside the Hill sphere, for example, if our moon were to wander too far away from Earth, then it would cross the Earth's Hill sphere and fall out of orbit of the Earth and fall into orbit around the sun. We're not going to derive this equation for the Hill radius or the radius of the Hill sphere, but we can apply it as well. So to find the Earth's Hill radius, for example, we would multiply A, the Earth's semi-major axis, or its mean distance from the sun, by the cubed root of the mass of the Earth over 3 times the mass of the sun. But we're not going to talk about the Earth today. We're going to talk about the outer solar system. The planets of the outer solar system are referred to as gas giants and ice giants. Jupiter and Saturn are the gas giants, and Uranus and Neptune are the ice giants. These planets are massive enough to keep hydrogen and helium in their atmospheres, and because the most abundant elements in the universe are hydrogen and helium, they are a lot larger in size than the terrestrial planets. But they are not massive enough to fuse hydrogen into helium and helium into carbon and other elements as the stars do. From the sizes and masses of these planets, we can infer their mean densities, and we find that Jupiter and Saturn are the lightest planets because their atmospheres are so thick with hydrogen and helium. whereas Uranus and Neptune have a greater portion of their interiors composed of ices such as water ice, ammonia, and methane. So with that in mind, we will proceed to the outer planets. Jupiter spins quickly on its axis in only about 10 hours, and it takes about 12 years for it to go around the Sun. Jupiter is only 1/1000th the mass of the Sun, but it is about 2.5 times all the other planets in our solar system combined. It's composed primarily of hydrogen and helium, but it probably has a rocky core with heavy elements, including iron. We don't know too much about the transition between its atmosphere and its core, but it probably has metallic hydrogen, which may be responsible for its powerful magnetic fields. We see the outer part of Jupiter's atmosphere and its atmospheric bands. We see storms like the Great Red Spot, which has been around for hundreds of years and is probably pretty permanent. We also see storms near the poles. We've even observed lightning in its atmosphere. We see aurorae near the poles as well due to its magnetic field. In 1994, we observed the comet Shoemaker-Levy 9 impact Jupiter. This comet had broken up prior to this impact, so it was able to impact Jupiter in a few different spots. There were impacts from other bodies in 2009 and 2010. So Jupiter is sometimes called a vacuum cleaner for our solar system. Pioneer 10 flew by Jupiter in 1973 and found plasma in Jupiter's magnetic field. It also found that the magnetic tail extends all the way to the orbit of Saturn. Voyagers 1 and 2 flew by Jupiter in 1979, and then the Galileo spacecraft orbited Jupiter from 1995 to 2003 before intentionally crashing into Jupiter. New Horizons then flew by Jupiter in 2007, and we currently have the Juno spacecraft orbiting Jupiter since 2016. The Galileo mission discovered faint dusty rings, which you can see in this image. As of now, Jupiter has 79 known moons. Most of Jupiter's moons are pretty small, though. It has 4 main moons, called the Galilean moons, because they were discovered by Galileo. These are Io, Europa, Ganymede, and Callisto. Ganymede is the largest moon in our solar system and is bigger than the planet Mercury. Io, Europa, and Ganymede are all in a resonance with each other. For every time that Ganymede orbits Jupiter once, Europa orbits Jupiter twice, and Io orbits Jupiter 4 times. This is called the Laplace resonance. Due to the extreme tidal forces that Io experiences, it is the most volcanically active body in our solar system. Europa has a subsurface ocean of water, and we are currently planning a mission, the Europa Clipper, to investigate that further. If there is another place in our solar system that has life, it might be Europa. Saturn spins on its axis almost as fast as Jupiter, about 10.5 hours, and orbits the Sun every 29.5 years. It's only about 30% the mass of Jupiter, but it's the next most massive planet after Jupiter. The first thing we notice about Saturn is its magnificent ring system, which we're going to talk about in a minute. Saturn is the least dense planet in the solar system. You may have heard that if there were a bathtub big enough, Saturn would float in it. This is based on the finding that its mean density is less than the density of water. Saturn's internal structure is probably similar to that of Jupiter. It has a pale yellow color due to ammonia crystals in its upper atmosphere. Its magnetic field is about 5% the strength of Jupiter's magnetic field. There are occasional storms in Saturn's atmosphere that we have captured. There's also a strange hexagon pattern near its north pole. Currently, we know of 82 moons of Saturn, the most of any planet in our solar system. Pioneer 11 flew by Saturn in 1979. The The next year, Voyager 1 flew by, and the year after that, 1981, Voyager 2 flew by Saturn. Then the Cassini-Huygens mission visited Saturn from 2004 to 2017, when it ended its mission by intentionally crashing into the planet Saturn. Saturn's main rings, the A ring and the B ring, and its faint rings, C, D, E, F, and G, have been named in order of their discovery. The rings are composed of small icy particles. The ones closer to Saturn orbit faster, so there's no way it could be a solid object. The rings are very wide, but very thin, only about 10 meters thick. Their structure is determined by the gravitational field, with gaps at resonance locations, spokes, wiggles, shepherding, propellers due to moonlets, and other subtle effects. There are many, many resonances in the Saturn system. Janus and Epimetheus are two co-orbital satellites that swap orbits every 4 years. The moons Mimas and Tethys are in a 4-2 resonance. The moons Enceladus and Dione are in a 2-1 resonance. Titan and Hyperion are in a 4-3 resonance. There are several small moons, Aegean, Methone, and Anthe, that Mimas keeps in resonance. And there are some resonances with moons that determine boundaries in the rings. Though Saturn has a lot of interesting moons, here we're only going to talk about 2 of them, Titan and Enceladus, which are 2 other objects in our solar system which could possibly have life. Titan is Saturn's largest moon, more massive than all of the other moons of Saturn combined. Titan has a hydrological cycle, not with water, but with methane. It evaporates, condenses in the atmosphere, and then rains down. It has lakes of methane and ethane near its poles, and it has a thick atmosphere. If I were on Titan and I could withstand the cold temperature, if I had wings fixed to my arms, I'd be able to flap my arms and fly. That's how thick the atmosphere is. Because Titan's atmosphere is so thick, from the outside, at visible wavelengths, we only see a pale haze. But with radar and other mapping, we're able to get a better idea of its surface. Also, the Cassini orbiter dropped the Huygens probe onto the surface of Titan in 2005, and it was able to take a picture. The Dragonfly mission is currently being planned to explore Titan. It is scheduled to launch in 2027 and arrive at Titan in 2034. Taking advantage of Titan's thick atmosphere, it's going to be a drone or sort of quadcopter. So hopefully we will learn a lot more about Titan in the next couple of decades. Enceladus is a smaller moon of Saturn, but it has active geysers at its south pole. This means it has a subsurface ocean of water. By the time that it spews this water out, it freezes into ice and goes into orbit around Saturn. These ice particles form the E ring. There are missions to Enceladus being proposed. So far, none of them has been approved, but that may change in the next few years. Uranus takes about 17 hours to spin on its axis and orbits the Sun in about 84 years. The first thing we notice is that Uranus is tilted sideways. Its obliquity is about 98 degrees, probably a sign that it experienced a large impact in the past that was able to tilt it. Uranus has a larger radius, but a lower mass than Neptune, because Uranus is less dense. It has an almost featureless atmosphere, though we have seen a little bit of activity near its equinox. Its magnetic field is very strange. It is not dipolar like the Earth's, Jupiter's, or Saturn's, and it is not axisymmetric. So we don't really know what causes this magnetic field, but it's probably not from the core, but from some intermediate region. Its atmosphere is extremely cold at about 49 Kelvin. Uranus has a ring system and 27 known moons. They are pretty small or mid-sized and tightly packed. So far, only Voyager 2 has flown by Uranus in 1986. Neptune spins on its axis in about 16 hours, and it orbits the Sun about 165 years. It has the strongest winds of any planet, up to 1,300 miles per hour. A great dark spot on Neptune, similar to Jupiter's Great Red Spot, was seen during the Voyager 2 flyby in 1989. Neptune has more internal heating than Uranus, so its atmosphere is slightly less cold, at about 55 Kelvin. Neptune's ring system includes ring arcs, which are incomplete rings. They're confined in longitude by some mechanism that we are not completely sure about yet. Neptune has 14 known moons, including one large moon, Triton, which has a cantaloupe terrain and is orbiting backwards or retrograde, so it will eventually crash into the planet Neptune. Astronomers had looked for Neptune because Uranus seemed not to be orbiting the way it should. It was being affected by some massive object beyond it. Similarly, it was presumed that Neptune was then not really orbiting as it should. So astronomers began to look beyond Neptune for some other massive body. In 1930, the American Clyde Tombaugh discovered Pluto. It was at first thought that Pluto was about as massive as the Earth, but then calculations in 1948 brought its mass down to comparable to Mars. Then measurements of its brightness in 1976 and the discovery of Pluto's moon Charon in 1978 allowed us to understand its real mass, only about 0.2% the mass of the Earth. Beginning in 1992, we started to discover lots of other objects orbiting the Sun near the distance of Pluto. We realized, similar to the asteroid belt, there is another belt of small bodies, now called the Kuiper Belt. This extends roughly from 30 to 50 astronomical units. These are small bodies and remnants of the solar system's formation. We now know of thousands of these bodies. It was especially because of the discovery of Eris in 2005 in the Kuiper Belt, which is more massive than Pluto, that the question was asked, should we add Eris to the list of planets now? Haumea had just been discovered in 2004, and Makemake had also been discovered in 2005, which were also possibly large enough to be included as planets. Should we add those as well? How many more objects are we going to discover? This made us want to reconsider the definition of a planet. So in 2006, the International Astronomical Union made an official definition of a planet. It has to orbit the Sun. It has to be massive enough to be rounded by its own gravity. That is, its shape should be determined by hydrostatic equilibrium. And the object must have cleared the neighborhood around its orbit. And that is something that Pluto has not done. So it was because of that third criterion that Pluto was reclassified as a dwarf planet. Also included among dwarf planets were Ceres in the asteroid belt, which is round due to its own gravity, as opposed to Vesta, and the other dwarf planets, Eris, Haumea, and Makemake. While I do agree that Pluto should not be considered a planet, I think that perhaps a better definition would have included some criterion based on the object's mass and location in the solar system. If we are to look at a plot of mass along the vertical axis by semi-major axis, or mean distance from the Sun, along the horizontal axis, we see that we can group the inner planets, Mercury, Venus, Earth, and Mars. We see that we can group the outer planets, Jupiter, Saturn, Uranus, and Neptune. And then Pluto is way down here. Does Pluto really belong with the outer planets? No, there is a better classification. It fits better with Eris, Makemake, Haumea. Ceres is over here. These other objects in blue are moons. So the Earth's moon, of course, that's not a planet because it doesn't orbit the sun. And then the Galilean moons, Titan and Triton. So perhaps looking at it this way might have been better, but either way, Pluto has found its real family among the dwarf planets in the Kuiper Belt. Beyond the Kuiper Belt is the Oort cloud, the outer part of our solar system. This is where the comets spend most of their time before quickly traversing the inner solar system. The Oort cloud goes to about halfway the distance to the nearest stars. If there were some small object in space, it's going to experience some gravitational pull. And if the nearest star is our sun, then it's probably going to orbit our sun, even if that orbit takes a very, very long time. So we have a much better understanding today of our solar system than we did when Pluto was first discovered. There's a nice order to it as well. We have the sun, the inner planets, the asteroid belt, the outer planets, the Kuiper belt, surrounded by the Oort cloud. It is likely that systems around other stars are similar in structure.